In a previous video, we talked about complex numbers and how useful they are for describing the geometry of 2D rotations. I called complex numbers the language of 2D rotation, and we saw how to use them to sneakily solve a tricky problem involving angular velocity. One of the main reasons complex numbers are so useful for solving problems involving rotations is that complex number multiplication corresponds to rotating and scaling a point. So they provide a very natural way to represent rotations algebraically. And right at the center of it all is Euler's formula, which gives a way to convert an angle into the corresponding complex number which, when multiplied, applies a rotation by that angle. The idea was that raising e to the power of theta I results in cosine of theta plus I sine of theta, which is the unique complex number that causes a point to rotate theta radians counterclockwise while keeping its distance to the origin fixed. But the real power and significance of Euler's formula comes from the fact that it's more than just a funky notation to represent a rotation by a particular angle. The expression e to the theta I behaves algebraically just like how real number exponentials work. Multiplying them together causes their exponents to add, and their derivative is just themselves times I. Exactly how it would work if I was a real number and we were dealing with a real-valued exponential function. But the drawback is complex numbers are only really able to describe rotations in 2 dimensions. They can't faithfully describe rotations in 3D or higher dimensions. So does that mean the algebraic elegance of Euler's formula is also limited to just 2D? Is the beautiful connection between the exponential function and rotations just a quirk of 2D space? Or can it be extended to 3D and beyond? That's going to be the goal of this video, to find an analog of Euler's formula that works for 3D and beyond that will allow us to algebraically describe and manipulate higher dimensional rotations using exponential functions and the familiar algebra and calculus rules they obey. At the end of the day, I don't think the underlying math involved here is actually all that difficult. But nevertheless, this is probably the most ambitious and mathematically demanding topic I've ever tried to cover in a video, and will require us to make several steep ascents to complete. I do think it's doable, and we'll take it slowly, step by step. But if you can make it to the end, I think the result will be well worth it, both because it's a really pleasing final answer, and because I think you'll gain some valuable new insights that will prove helpful in understanding more advanced topics in modern math and geometry. So I ask that you buckle up and be ready to pause the video when you need to let it sink in. Okay, deep breath, let's go. Part of the reason complex numbers and the regular Euler's formula can't describe 3D rotation is that, unlike in 2D, 3D rotations don't compose commutatively. That is, the order in which you perform 2 3D rotations matters. For example, if I take this cube and first rotate it so its front face is on top, then twist it 90 degrees clockwise about the vertical axis, I get a different result than if I do the same 90-degree twist first, and then flip its current front face upward. The reason this can happen is because in 3D and beyond, rotations can occur in multiple different planes. Like in this cube example, one of our rotations was in the horizontal plane, and the other was in a vertical plane. This isn't an issue in 2D because there's only one plane of rotation there, the whole space itself. So the order in which you perform multiple rotations doesn't matter. This clues us in as to why complex numbers really can't be expected to describe 3D rotations. Because complex number multiplication is commutative. The order in which you multiply 2 complex numbers never matters. So if complex numbers can't represent 3D rotations, what kind of objects can? What objects might care about the order in which you multiply them? Well, there are actually quite a few different options at this point, kind of depending on your mathematical taste, it would seem. A standard choice is the quaternions, whose multiplication is famously non-commutative. But there's also matrices, as well as fancier objects like multivectors and geometric algebra. But for this video, I'm going with traditional matrices, since many people know at least a little bit about them, and will be more comfortable with them coming in fresh to a video like this compared to the other tools. But I know there's a lot of overlap with other fields here, and there will probably be many concepts from those fields that I'll brush against and not always acknowledge. Alright, so how can matrices represent rotations? Matrices show up in the branch of math known as linear algebra, the study of vectors and how they behave when transformed by these things called linear transformations. Linear transformations are basically functions that map vectors to vectors in such a way that scaling the input scales the output by the same factor, and adding any two inputs results in the corresponding outputs getting added. This means linear transformations are completely determined by their behavior on the basic unit vectors, such as 1, 0 and 0, 1 in 2D, since where a vector like 3, 2 ends up after a linear transformation will equal 3 times where the x unit vector 1, 0 lands, plus 2 times where the y unit vector 0, 1 lands, because the vector 3, 2 can be written as 3 times 1, 0 plus 2 times 0, 1. For short, we usually abbreviate these basic unit vectors as I hat for 1, 0 and j hat for 0, 1. Matrices represent linear transformations in that taking a matrix and multiplying it by a vector expressed as a column matrix applies a linear transformation to that column vector. The linear transformation it applies can be read off the columns of the matrix. The first column tells you where I hat lands. The second column tells you where j hat lands. Now, matrices, or linear transformations, can be visualized like this. Instead of thinking of vectors as arrows, think of them as points in a grid space. Then applying a matrix to all the points in the space warps it in such a way that the origin stays fixed in place, and parallel lines remain parallel and evenly spaced. Or to put it another way, every grid square gets warped into identical parallelograms, but the origin point doesn't move. Finally, multiplying two matrices together corresponds to composing the linear transformations they represent. That is, applying the product of two matrices A and B to a vector yields the same result as having first applied B to that vector and then applying A to that vector afterward. Now, if we think about applying, say, a 90-degree counterclockwise rotation to the plane, you'll notice that the grid lines remain parallel and evenly spaced. In fact, they don't change at all, except for being rotated, of course. That means rotations are linear transformations, and we can find what matrix describes it by looking at where the basic unit vectors I hat and j hat end up after being rotated. I hat gets moved to where j hat was, 0, 1, and j hat gets moved to -1, 0. So we'll make these coordinates the columns of our matrix, and voila, we have our rotation matrix. And you can check that multiplying any 2D vector by this matrix rotates it 90 degrees, the same as if you had multiplied the corresponding complex number by I. So this matrix plays the same role as the imaginary number I in the complex plane. Now, in Euler's formula, we take E and raise it to the power of I, the 90-degree rotator, times theta in order to generate any other rotation in the plane. So if we're going to generalize Euler's formula beyond 2D, it sounds like we'll need a way to raise E to the power of a matrix. Let's look into that now. The key to finding a way to raise E to the power of a matrix is to find a way to express the regular e to the x function in a form that can work for matrices. If you know your calculus, you might remember that e to the x can be represented with the Taylor series 1 plus x to the 1 over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on. If we rewrite the initial 1 as x to the 0, the formula becomes completely compatible with square matrices, and so we can simply define e to the power of a matrix to be the value of this infinite series for a matrix input, and where the 0th power of a matrix is taken to be the identity matrix I. Now, whenever you define something using an infinite series, you always have to be careful to justify that the series converges for the inputs you care about. But I'll skip over that here and just tell you that it does indeed converge for any possible square matrix you might plug in. But this still leaves open the question of how to interpret or visualize what this operation is really doing to a matrix. Sure, we can calculate it, at least in principle, using this infinite series, but what does it mean? As a matter of fact, there's actually an elegant visualization for what a matrix exponential is doing that 3Blue1Brown covered superbly in a video. A visualization too good not to borrow for this video. So I'll go over it briefly here, but I definitely recommend you watch his whole video if you'd like a fuller picture of the matrix exponential. The idea is to view the matrix A in the expression e to the a as defining a certain velocity vector field on all points in the space. The velocity vector at a particular point is defined to be a times the position vector of that point. Then for a given time value t, multiplying a position vector r by the matrix e to the at returns the location r ends up after traveling t units of time flowing along that velocity field. For our 90-degree rotation matrix R, it would associate every point in the plane with a velocity vector pointing perpendicular to the line connecting it to the origin, whose magnitude exactly matches its radial distance from the origin. This precisely describes the movement of points orbiting the origin at a speed of 1 radian per second. Thus, the matrix exponential e to the rt applied to a point r will return its position after t seconds orbiting the origin, which will be an angle of t radians away from where it started. So we've just managed to reproduce the behavior of the complex exponential function, but for matrices. An excellent start. But, of course, matrices can be used to describe transformations in more than just 2 dimensions. So let's see if we can extend this to describe 3D rotations with exponentials. Based on the 2D example we just did, it looks like the trick to getting an exponential function to compute an arbitrary rotation is to plug a 90-degree rotation into it, scaled by the angle of rotation you want. After all, that's what the original Euler's formula for complex numbers is doing. It takes a scaled version of I, the 90-degree rotator in the complex plane, and converts it into a rotation by a different angle. Just to make sure we're on the right track, let's test it out for a very simple 3D rotation, a rotation of the xy plane about the z-axis. Since we're dealing with a 3D space, we now have 3 basic unit vectors, I hat, j hat, and also k hat, the vector 0, 0, 1, pointing 1 unit in the positive z direction. Performing a 90-degree rotation about the z-axis will rotate I hat and j hat similarly to before, but leaves k hat unmoved, since k hat is the axis of rotation in this case. So the matrix that describes this rotation is given by this 3x3 matrix, which I'll call Rxy, since it's a rotation of the xy plane. Alright, now let's plug in t times this matrix into the matrix exponential, and I'll get the computer to apply the resulting matrix to this cube for increasing values of t. If we've done our job right, we should get a gradual rotation of the cube about the z-axis. And... Whoa, whoa, whoa! Stop, stop, stop! What the heck are you doing? Go back to the beginning. Okay, now increase t again, but do it slowly. Okay, well it looks like we're kind of getting the rotation we want. The cube does seem to be twisting about the z-axis, but, of course, it's also getting itself stretched horribly out of shape along the z-axis. Why is it doing that? Let's try to analyze it using our visualization trick for matrix exponentials. Just looking within the xy plane itself, our 3D rotation matrix, Rxy, produces a velocity field exactly like the one we saw in the 2D case, a synchronized counterclockwise flow around the origin. However, unlike the 2D case, this velocity field also has a z component. And if we take a view outside the xy plane, we see that the flow kind of spirals away from the xy plane with greater speed the further away it is. If you think about it for a second, this should make sense. The velocity vector at a point comes from applying the rotation matrix Rxy to it, which will rotate the position's x and y components, but will leave its z component unchanged. The velocity field we really want is one that swirls around the z-axis, but where the z component of every velocity vector is 0, so that it stays parallel to the plane of rotation. In other words, in addition to rotating our position vectors, we also need to project them onto the rotation plane. For this basic example, it's actually pretty easy to make this happen. We just need to change the third column of our rotation matrix to be the 0 vector. This will cause the matrix to collapse a vector z component to 0, in addition to rotating its x and y components. Using this modified matrix in our matrix exponential formula, it now acts exactly like we would hope. It purely rotates the cube about the z-axis by an angle equal to our t-value. So this seems to be the key insight. To get a rotation matrix out of an exponential, you have to plug in a matrix that applies a 90-degree rotation within the plane of rotation you want, but also performs a projection onto that plane of rotation, so that the velocity vectors of the intended rotation are parallel to the rotation plane. And the reason why it was simpler in 2 dimensions is because in 2D, there's only one possible plane of rotation, and all points are already inside it. So there's no need to project vectors onto that plane, and we can simply plug in a raw 90-degree rotator into the exponential. So at a more fundamental level, it seems exponentials don't so much turn 90-degree rotations into general rotations, but it's more that they turn 90-degree rotation projections into general rotations. It's just that in 2D, the projection aspect is hidden from us. Okay, this is nice and all, but it still requires us to manually set up a 90-degree rotation projection matrix to plug in to the matrix exponential. In the case of rotating about one of the primary axes, x, y, or z, this isn't too hard. But what if we want to express an arbitrary rotation about an oblique axis as an exponential? Like, for example, a rotation within a plane defined by a pair of vectors, u and v, that could be oriented anywhere in the space. And anyway, one of the main reasons we're doing all this is to find a nice, compact way to express more complicated rotations in 3D and beyond using an Euler formula like syntax. It'd be awfully clunky to have to plug in these massive 3x3 matrices literally into our exponential expressions. So let's see if we can find a more elegant way to describe these planes of rotation and the rotation projection matrices on them. Those of you with a background in physics might have an idea for how we can project and rotate a vector by 90 degrees in any plane. It turns out there's a sneaky way to do it, at least in 3D, using the cross product. If you're unfamiliar, the cross product is a way of multiplying two vectors, u and v, usually in 3D, to generate a third vector perpendicular to both, whose magnitude is given by the product of the magnitudes of u and v individually times the sine of the angle between them. And the direction it points is given by the right-hand rule, which basically says the cross product vector is placed so that if you orient your eyeball directly above it, the vector v should lie in a direction counterclockwise from the vector u. The key feature about the cross product that will be useful for us is that the result of cross-producting two vectors is always a vector perpendicular to both. That is, a vector 90 degrees away from the others. This means that if you're clever about it, you can get the cross product to perform a 90-degree rotation for you in any plane you want, such as in the uv plane in the direction from u toward v. To see how, let's first take the vectors u and v to be unit length and perpendicular to each other, so we can ignore any scaling effects from taking their cross product. So the cross product, u cross v, will be a unit vector perpendicular to the uv plane, oriented so that looking down on it, v is offset counterclockwise from u. Let's call this unit vector w for short. But if we now take our vector r and cross product it on the left by w, we'll get a new vector perpendicular to both r and w. But since w was already perpendicular to the uv plane, any vector perpendicular to it will be back inside the UV plane. And since W cross R is perpendicular to R as well, it must be a 90-degree rotation of R within the UV plane. Moreover, if R was not originally contained within the UV plane to start, the result will still be in the UV plane, but R will be scaled exactly as if it had been first projected onto the UV plane. So the cross product, W cross R, does exactly what we're looking for. It projects R onto the UV plane, and then rotates it 90 degrees in the direction from U toward V. Now remember that W is really just an alias for the cross product of U and V. So really, we found that the triple cross product, U cross V cross R, performs the projection rotation we want. But, you might remind me, our matrix exponential needs to take a matrix as input, not a vector. So we need a way to express this triple cross product in terms of a matrix multiplication. Luckily, there is a way. It turns out any cross product, A cross B, can be equivalently represented by multiplying B by a certain matrix. I won't go through the details here, but it turns out if you multiply B by this matrix, built from the components of A, the result is identical to have taken the cross product A cross B. In our case, the vector A is itself a cross product of two other vectors U and V, so its corresponding cross product matrix looks like this. Now, I know it looks like an absolute nightmare of a matrix, but the good news is it can be rewritten in much simpler fashion. First, it can actually be decomposed into the difference between these two matrices, and each of these can be thought of as coming from multiplying one of the vectors U or V as a column by the other as a row. If we think of U and V as column vectors, then the cross product matrix of the cross product, U cross V, can be expressed as VU transpose minus UV transpose, where transpose means the matrix has had its rows and columns swapped. This odd way of multiplying a column vector by a row to get a matrix is called taking their outer product, which is in contrast to what's called their inner product, which is where you multiply a row on the left by a column on the right to generate what is equivalent to their dot product. Now, when taking the difference between two oppositely arranged outer products in this way, the resulting matrix always has a special form. The diagonal entries will all be 0, and entries on opposite sides of the diagonal will always be negatives of each other. In fact, taking the transpose of this matrix, swapping its rows and columns, does the same thing as simply negating the matrix, flipping the signs of all its entries. Matrices like this have a special name. They're called skew-symmetric matrices. As a brief side note, it turns out what we have here is essentially a special case of a more general construct known as a wedge product. It's not exactly the same thing. Wedge products are usually thought of as a more abstract kind of entity than just a simple matrix, and when they are represented as matrices, they often do the subtraction in the opposite order than what we're doing. But all that's just by the way. I just want you to know we're passing very close here to a pretty big rabbit hole that I'm not going to get into in this video. Anyway, I think we've now found what we were looking for. Up to a possible scaling factor, the skew-symmetric matrix produced by this difference in outer products performs a projection onto the UV plane, and then performs a 90-degree rotation from U toward V. Exactly the matrix we would want to plug in to the matrix exponential to turn it into an arbitrary rotation. Such a matrix could be called a rotation generator, since exponentiating a scaled version of it generates a rotation by any angle in the UV plane. Now, it'd be nice to have a name for this way of combining two vectors, U and V, to get this rotation generator matrix. But seeing as it's neither exactly a cross product nor a wedge product, and I also don't want to overload those names, I'm going to give it a name of my own. I call it the tilt product, since the matrix it produces can be thought of as tilting vectors 90 degrees from U toward V, along with projecting them onto the UV plane. And I'll represent it with the notation U cross V surrounded by angle brackets, which you can read as U tilt V. Now, if u and v are perpendicular unit vectors, we can express a rotation by theta radians within the uv plane in the direction from u toward v as e to the power of theta times u tilde v. So for example, a rotation in the xy plane can be written as e to the power of theta times I hat tilde j hat. Likewise, a rotation in the yz plane is e to the power of theta times j hat tilde k hat. Isn't that satisfying? It looks and feels just like raising e to the theta I back in the complex plane. Except now we have a way to express I for any possible rotation plane in 3D or even higher dimensions. So in some sense, we found a more general Euler's formula that works beyond 2D. One thing to keep in mind about this notation, though, is the order in which you tilt two vectors matters. Just like the cross product, swapping the order of a tilt product negates the result. So j hat tilde I hat is the same as negative I hat tilde j hat, which should make sense because j hat tilde I hat means tilting from j hat toward I hat, the opposite direction from tilting from I hat toward j hat. But I also want to stress that although the tilt product looks and acts a lot like a cross product, it's really not inextricably tied to it anymore. Since we can express the tilt product in terms of a difference in the outer products of two vectors, and outer products aren't restricted to dimension 3, this formula can actually be applied to any pair of vectors in any dimension. It just so happens that in 3 dimensions, the tilt product can be interpreted as literally calculating the cross product matrix of a literal cross product. But in other dimensions, we can simply take the entire expression as a whole to refer solely to this difference in outer products, which doesn't care about the dimension of the vectors. So in some sense, this characterization is probably more fundamental than the cross product one. Now, there's still a whole lot more to say about rotations and their relationship to the matrix exponential. More than could fit in a single, already pretty long video. So I think we'll stop here for now, and continue with more in a follow-on episode or two, where, among other things, we'll derive a formula that greatly simplifies computing the matrix exponential for one of these tilt product matrices, and which delightfully mirrors, though with some interesting key differences, the classic Euler's formula for complex numbers. We'll also investigate what needs to change if we want to describe a rotation with two vectors u and v that aren't necessarily perpendicular or unit length. And we'll also explore what it's like to do algebra and calculus with matrix exponentials in the mix, which was kind of my whole reason for trying to express rotations using them. I'm hoping to release a follow-on video in the not too distant future, and so if you're interested and would like to be sure not to miss it, consider subscribing and/or enabling the bell notifications. I don't normally like to mention subscribing very much, since I know it can get annoying, but this time it seemed relevant enough to bring up. Plus, if you made it to the end of this video, you'll very likely enjoy the follow-on. In the meantime, though, if you'd like to sink your teeth into some math or science right away, then you'll probably get a lot out of this video's sponsor, Brilliant.org. Math, perhaps more than any other subject, is highly cumulative. Higher-level math often doesn't make much sense without a strong foundation in the lower, and Brilliant is an excellent resource for bolstering that foundation. Like in this video, we built up to a 3D Euler's formula by heavily relying on tools from linear algebra like matrices and linear transformations. Topics that Brilliant actually covers quite thoroughly in a 2-part course on linear algebra, even up to some pretty advanced topics like wedge products, which I couldn't really talk about in this video. But whatever level you're at, Brilliant likely has something for you. Their selection of courses are as wide as they are thorough, ranging all the way from basic algebra to calculus to group theory, along with other subjects besides, like computer science and data science, all of which are taught interactively, which is key to learning a topic deeply. To get started with a free 30-day trial, head over to brilliant.org/morphocular, and the first 200 of you to sign up will get 20% off an annual premium subscription. So thanks to Brilliant for sponsoring this video, and thanks to you for watching.